All right, on this problem, what we want to do is we want to locate the extreme values of the function and where they occur. So in order to find extreme values, you're going to have to look at a derivative. And in order to get that derivative, I think the easiest way to do that on this particular problem is to go ahead and use the quotient rule. And just a quick refresher, quotient rule is low d high minus high d low over low low. And remember, with extreme values, we want to look for where we are either undefined or equal to 0. So after we take our derivative, we're going to set both parts equal to 0, okay? The top and the bottom. So the derivative of this guy is going to be low, x squared plus 1, d high, which is 4, minus high, which is 4x, d low, which is 2x. And I always use brackets when I use the quotient rule. I don't want to accidentally lose track of something that should have a negative sign on it maybe. With x squared plus 1, we don't really need to square this out. We can just write it this way, x squared plus 1 times x squared plus 1. And this will get us what we need to get. So clean up the top now. We're going to have 4x squared plus 4 minus 8x squared over x squared plus 1 squared. And one more step on the top and we'll be done. Go ahead and combine together the things that have the same variables and exponents. So 4x squared minus 8x squared. So negative 4x squared plus 4 over x squared plus 1. Now, squared. What we want to do is we want to discover where the top equals 0, negative 4x squared plus 4, and where the bottom equals 0. And we can just work with that x squared plus 1 part. We don't need to worry about it being squared out. So over here we're going to have negative 4x squared equals negative 4. We're going to have x squared equals 1. And we're going to have x equals plus or minus 1. On the other side, we're going to have x squared equals negative 1. Now, imaginary numbers are really, really important, but we're not going to worry about imaginary numbers when we're looking for extreme values. So this guy actually we don't have to worry about at all. So the question is, where do the extreme values occur? Our answer is they occur at x equal to 1 and negative 1. So if we want to know the exact point that these values occur at, then we would say, hey, we want to know f of 1, which is 4 times 1 over 1 squared plus 1, and we would want to know f of negative 1, which is going to be 4 times negative 1 over negative 1 squared plus 1. So we're going to end up then with 4 over 2, which is 2, and we're going to end up with negative 4 over 2, which is negative 2. And these give us our extreme values for this problem. Alright, on this problem we're told to find the derivative of each critical point. We're told that those critical points can only be larger than 0 or equal to 0, and then we want to determine what the extreme values are at that specific point. So there's a couple different ways to do this problem. I found it easiest to go ahead and multiply through the x to the 2/3. Remember, when you multiply through with exponents, you're going to add them. So 2/3 plus 1, this is how it would be. Well, that's going to end up being 6/3, and that turns out to be 8/3. So what I'm going to end up with is y equals x to the 8/3 power minus 9x to the 2/3 power. And I just found for this particular problem, this was the easiest way to attack it. You could do several different things. You could use product rule and get the same exact answer. So the derivative is going to be 8/3 x to the, and then subtract 1, which is 3/3. So 8/3 x to the 5/3 minus, and then 18 thirds, which would be 6, x to the negative 1/3. Now, what I did here was a little bit different. I went ahead and factored out the lowest possible degree of x, which in this case is x to the negative 1/3. Now, if you're not super comfortable with that, it could be a little bit weird what I'm getting ready to do, but watch this, because when we distribute, we'll get back to where we started. So I'm going to factor out a 2x to the negative 1/3. Now remember, when you factor something out, you're subtracting. So 5 minus negative 1/3, okay, 5 minus negative 1/3, that's going to be 5 plus 1, which is 6/3, okay, which is 2. So this is going to give me then 4/3 x squared, which I like. And then on the back side here, 1/3 divided by 1/3 is cancels that one out, and 6 divided by 2 is 3. And I felt like this was a lot easier to solve this problem from this spot. And if you didn't catch quite what I'm going with here, go ahead and distribute the x to the 1/3, negative 1/3 back through. You'll end up right back where you started, which was 8/3 x to the 5/3. It's kind of a cool little trick here, and one to just keep in your back pocket, because every now and then we're going to want to use it. Well, what that gives us is 2 over x to the 1/3 times 4/3 x squared minus 3. And if I'm going to find these critical values, I need to set all of this equal to 0. And 2 over x to the 1/3, when I set that equal to 0, the numerator doesn't change, the denominator becomes 0, so I'm undefined when x is 0. That's my critical point for this guy. And then when I do 4/3 x squared minus 3 equals 0, I'm going to add 3 to both sides. So 4/3 x squared equals 3, 4x squared equals 9. I'll just go right up here, get a little more room. X squared equals 9/4. And then take the square root of both sides. X equals plus or minus 3/2. So the critical points then are points that are going to be greater than or equal to 0. So the critical points for this particular problem are going to be 0 and positive 3/2. So if we're going to discover what those critical points are, what the values are at that point, we're going to just substitute them in to our original function. F of 0 is going to be 0 to the 2/3 times 0 squared minus 9, which is 0. And on the other side here, f to the 3/2, which is going to be 3/2 to the 2/3 times 3/2 squared minus 9. And I went ahead and punched this in on my calculator because it's I don't carry around all these different fractions in my brain. So when x is 3/2, our y value in this case is going to be negative 8.845. And you can double check me, punch that into your own calculator, make sure I did it right. So in this case we were looking at a max value here, and in this case we're looking at a min value of the original function here. Alright, so with this problem we want to look at the mean value theorem, and just on this particular interval whether this function works. And in order to work, we've got to be able to take a derivative at every point. It's got to be a closed interval, and it's got to be a continuous function. So we're just going to look here at x to the 1/3 power, take the derivative of that guy, and what we're going to find is this becomes 1 over 3x to the 2/3 power. Well, we can't actually take a derivative at every point, because when we're at 0, which is on our interval, we're going to wind up with an undefined situation. So when I put a 0 in down here, I'm going to end up with an undefined problem. And because I cannot take a derivative at every point, find that derivative at every point inside the interval from -1 to 5, this does not pass the mean value theorem. Now, the other thing that you could do is go ahead and look at the graph of this guy. And if memory serves, I think the graph looks something like this. And so what happens is, right here as we go through the origin, we're going to have a vertical tangent, and that's one of the 4 places where you cannot take a derivative. So if we just look at that original basic function, we'll see that it fails the mean value theorem test. Alright, with this problem, we want to actually use the whole mean value theorem process, and we want to find the specific value of x on the interval from -2 to 1, where our derivative is equal to the slope of the line that goes through x values of 2 and x values of 1. So what we're going to have to do is a couple things. One, we're going to have to take derivative of x. And when we do that, the derivative of f of x is 2x plus 4. The derivative of 4 is 0, so 2x plus 4. And then what we have to look at then is we need to look at f of -2 minus f of 1. That's backwards. We need to look at f of 1 stop minus start, f of 1 and then f of -2 over 1 minus -2. So we've got to work this part out, because what we're going to do is we're going to set this is old-fashioned slope right here in pink, and we're going to set this old-fashioned slope for this x value and this x value. We're going to take that old-fashioned slope, we're going to set it equal to 2x plus 4. So what I'm going to have is 1 squared plus 4 times 1 plus 4 minus, and use brackets here because we don't want to lose that minus sign along the way, -2 squared plus 4 times -2 plus 4. Just got it. All right. All over. And then 1 plus 2 is 3. So I'm going to have 1 plus 4 plus 4 on the outside. I'm going to have 4 minus 8 plus 4 on the inside. I'm going to double check my notes. Yep. And so what that's going to give me is 1 plus 4 plus 4, that's 9. 4 minus 8 plus 4, that's 0. So I'm going to end up with 9 divided by 3, or 3. And so what I want to do, I want to set my derivative equal to the slope of a line through the points that have x values of -2, 1. And this will satisfy our mean value theorem. So I'm going to go ahead and subtract 4 from both sides. And x is equal to -1/2. So at that specific value, this is where my average of my graph, average of the function, occurs when x is equal to -1/2. Remember, mean value, mean just means average. So that's what we're trying to find with this guy, the average of all the y coordinates, and that occurs when x is equal to -1/2. If we wanted to find out what that y value is, then all we need to do is substitute in the -1/2 into the original function and check it out. So it would look something like this: -1/2 squared plus 4 times -1/2 plus 4. And I'm going to be a super happy guy, and I'm not going to work that out. I'm going to let you finish it, okay? But that's how you use the mean value from start to finish, the whole mean value theorem process. All right, on this question, we want to use analytical models to find the local extrema. So derivative, that's what we've got to do. We've got to take the derivative, then we're going to create a sign chart, and we're going to look for where the sign changes. And quotient rule is what I'm going to prefer on this one. If you want to use the product rule and change the whole denominator around to a -1 value as an exponent, that's fine too. You can do it both ways. Okay, we'll get the exact same answer. So the derivative of the top is 1 times the bottom, so low d high minus high, which now is x minus 1, d low, and that's going to be 2x plus 3 over low low. So again, this is going to be a situation where I don't necessarily need to go ahead and square out x squared plus 3x plus 5. I can leave it because I'm just interested if this x squared plus 3x plus 5 equals 0. That would be an undefined point, and that could be a possible critical value in my original function. So when I solve this guy out, I'm going to end up with x squared plus 3x plus 5, and then minus, and then inside I'm going to have 2x squared minus 3, and then negative 2x plus 3x. So I'm going to have this guy. I'm going to go ahead and leave the bottom exactly how I wrote it here. So this is just going to be x squared plus 3x plus 5 squared. All right. Combine the tops down, and what we're going to end up with is x squared minus 2x squared, so that's negative x squared. 3x minus x, so plus 2x. And 5 plus 3, 8. All right, so here's my function. I don't think x squared plus 3x plus 5 factors, and I don't think it will ever equal 0. So I don't have to worry about that guy. Let me just double check my notes, and let me double check my notes. Yeah, we're not going to have to worry about him. So what I am going to do though is set the top equal to 0. I'm going to let negative x squared plus 2x minus plus 8 equal 0. I'm going to go ahead and divide out a negative 1. You can do this because I'm going to do it on both sides. Negative 1 times 0 is 0. And this is a cool little trick that will help me factor my problem. I can factor this guy a lot easier than I can factor the negative x squared guy. And when I do this, remember, we're only interested in where it crosses the x-axis. That's why this works. So I'm going to have x minus 4 and x plus 2. Now, sign chart time. And what I'm going to do is I'm going to take the two values that make a 0 in my derivative, okay? And that's going to be negative 2 and positive 4. And I'm going to list them on a number line. And then I'm going to write down all the factors that I am working with on this problem. And so that's going to be a negative, because I'm going to look right here. So I'm going to have x minus 4. And I'm going to put my negative back now. He's really important on this part. Okay, so I need to work with basically my original factoring. So if I factor out, what I'm doing here is factoring out a negative. So that this is what I'm working with. Okay, so negative x plus 4, x plus 2, and then I do need my denominator. Even though it'll always be positive, it could come in handy. So I'm going to go ahead and write that down. X squared plus 3x plus 5 squared. All right. Now, pick a number less than negative 2, like say negative 3. And when I put negative 3 in on this guy, I'm going to get a positive value. I don't care what the number is. I just need to know is it positive or negative. I'm going to put a negative 3 in here. I get a negative value. And anytime you square anything, you're going to get positive. So that's using negative 3. I'm going to take a 0 from in between negative 2 and 4. I'm going to take a 0. So when I put a 0 in, that's going to get me a positive again, and then a positive here, and then a positive here. And then lastly, with the 4, I'm going to put like a number like 5 in. That's going to give me a negative. It's going to give me a positive, and it's going to give me a positive. So big picture, if I take a positive number times a negative number, times a positive number, I get a negative. If I multiply everything with positives, I get positive. And over here, I'm going to get a negative. So what's this tell us about our graph? It tells us that our graph is decreasing here, it's increasing here, and it's decreasing here. Well, what does that mean? That means that we're going to have a max value when x is equal to 4, and we're going to have a min value when x is equal to negative 2. Okay? Why? Because I decrease and then increase. If I decrease and then increase, I have a minimum. If I increase and then decrease, I have a maximum. So when on question 10, when they ask us to find the local extrema, this is how I do that. And then I check these in my original function to figure out what y values match. And so I did that. You can punch it into your calculator or however you want to do it, but you can just take 4 minus 1 over 4 squared plus 3 times 4 plus 5. That's one guy. I'll let you punch him in to find that specific y value. The other one that you're going to do is you're going to use negative 2 plus minus 1, negative 2 minus 1 over negative 2 squared plus 3 times negative 2 plus 5. So these are the two things will give you the y values that you need to find the max and mins at that spot. And so that's how you use a derivative to find these critical points in areas where your curve is increasing or decreasing.